Okay, hello everybody. So my name is Camilo. I work at Factor, and today I'm going to talk about optimization problems in Python using Pyomo. This is going to be an introduction. So let's go. Okay, so first, this is how the talk is structured. So first we will look into an introduction of optimization problems and Pyomo, and then we will see how Pyomo deals with some problems with two examples: the warehouse problem and the Sudoku problem. So let's begin. First, we need to define what is an optimization problem. Okay, so here we're going to define an optimization problem with three main components. So we have the objective or the goal, which is the thing that we want to optimize. So we want to minimize cost, maximize profit, maximize income, and so on. And there's also a kind of different problem that it's to know whether a problem is feasible or not. And we see it later. And another component is the constraints or relationships. So those relationships are between parameters and variables, and are kind of like the constraints or requirements that our problem must satisfy. So for example, we can only have 10 machines, the prices are strictly positive, and so on. And finally, we have our decision variables, which are the things that we tune to know how they relate between each others and to trying to optimize that objective or goal, right? So some example of decision variables are the number of machines that I have to use, an indicator if I can use that machine or not. We can have an indicator of the prices. If I put the price up, what will happen, and so on. And we can see here that this thing is independent on the way we solve it. So here we are not taking into account solvers and things related to it. And this is what Pyomo does principle. It just helps you a lot on the formulation and the definition of the problems. Okay, so let's continue. So what is Pyomo and why Pyomo? Okay, so Pyomo, it is a Pythonic library. It's object-oriented and it's open source. It was developed by Sandia National Laboratories, which is kind of like a nuclear thing related to United States, a research laboratory or something like that. And it's part of the COINOR organization, which is focused on operation research problems and things related to it. Okay, so what else that has Pyomo? So Pyomo has some customized capability, so you can build kind of blocks and plug them in and connect them. That's kind of an advanced feature of it. Also, as I told you before, it is solver agnostic. It doesn't care the way you solve it. It's just the core of it is how you formulate it and how you define that problem. And then you can use multiple open source or commercial solvers like Ample, IPOPT, GLPK, and many other solvers. It has a high-level API, so you construct your model in Pyomo, and then it will just compile it to a solver so it can translate it, so the solver can solve it. And it has a fantastic documentation. It has a lot of examples and really nice notebooks where you can see multiple approaches on how Pyomo solves many problems. And finally, it can tackle really advanced optimization problems like mixed integer programming, mixed integer nonlinear programming, discrete programming, nonlinear programming, stochastic programming, disjointing programming, and so much other advanced optimization problems. Okay, let's continue. Okay, so what are kind of some sample applications that Pyomo can help you to do? So here I have some examples, but there are many more other applications. Some of them are, for example, job scheduling, when you need to schedule like for example, the machines, how machines should do a product and so on. So that could help you on it. On logistics and transportation, optimization of paths and many related things, industrial production, portfolio optimization, and so many others. Okay, so let's begin with an example. So let's use Pyomo. Okay, so we will see here the warehouse problem, which is kind of like a pretty standard and like a basic use of Pyomo and an example of Pyomo. We will do three things. First, we will define the problem, then we will formulate it, and finally, we will use Pyomo to solve it. So let's dive into it. Okay, so what's the problem? So let's suppose that we have 5 countries. For example, Guatemala, Panama, Colombia, Peru, and Brazil. Yeah, and we have 4 possible warehouses or cities that we are going to locate them. So, for example, we have here Ciudad de Panama, Bogotá, Peru, or Rio de Janeiro. And we have like a requirement that we cannot build all the warehouses. We only can build a limit. We don't know the limit yet. Okay, and the third requirement that we have is that we need to define from each warehouse how much demand should that warehouse provide to each country. So for example, Bogota will attend 60% of Peru's demand, or Bogota will attend 100% of Colombia's demand, and so on. Another thing is that we have costs, right? So we have a cost of delivering from Bogota to Peru, from Bogota to Brazil, and so on. We will see later those costs, and those costs are proportional to the demand fraction that we are attending. So if the demand that we're attending from Brazil, from Bogota is 100%, so our cost will be 100%, and so on. And finally, the thing that we are telling to do is that we need to minimize the cost of delivering from the warehouse we pick and meeting all the demand from all the countries. We have to fulfill all the demand of all these countries, right? So now we have defined the problem. So let's see. Now let's formulate it in our three main components. So first we have an objective. So as we see, the objective is that we need to minimize the cost fulfilling the demand. Okay, and we have a set of constraints. So let's look at them. So first, we must ensure that all the demand is satisfied for each country, right? That's the thing that we have said before. And second one, we need to ensure that we have a limit of warehouses. We cannot build all the warehouses. We have to build, for example, 2 or 3 warehouses. Another thing is that the demand is a fraction. So it's just going to be a number between 0 and 1. We are going to attend 20% of the demand from Colombia to Peru, or from Colombia to Panama, and so on. And we have another constraint that we can build or not build a warehouse. So there are only 2 possibilities. So that would be kind of like a binary variable, right? And finally, we must ensure that you can only use that built warehouses. So you cannot use a warehouse that was not built, right? Because you are not producing anything there, right? And finally, what are our decision variables? So we have 2 decision variables. So first is which warehouses are we going to pick? Which are we going to use? Are we going to use Ciudad de Panama, Rio de Janeiro, Bogota, or Lima? And we have to define how much fraction each warehouse is going to attend of each country. So we need to define if Bogota is going to attend 50% and so on. Okay, let's keep going. So let's look at Pyomo. So Pyomo has 2 modeling approaches. So it has the concrete model and the abstract model. So with the names, we can figure out what it means, but let's look at it. So on the concrete model, we have the data, and then we pass the data to the model. So we have kind of like built the model, and then we pass that to the solver. So here, the data is kind of like defining the dimensions and the thing of our model, and then we pass it to the solver. And on the abstract model, it's kind of like we first define the model, the relationships they are going to have, and then we pass on data and construct the model. So kind of like we instantiate that object, and then we pass that object into a solver, and we solve the problem. We can see pretty good here, kind of like the definition. On the concrete model, we have predefined our parameters. So we know that it's 2, 3, whatever. And on the abstract model, we have non-defined anything. We do not know the shape of X. We do not know the values of C, and so on. So let's keep going. So first, we're going to solve our warehouse problem with a concrete model. So let's dive into it. Okay, so here we have a problem. Here we have like some data. I will just show you what it looks like. So here we have defined our kind of like parameters and variables that we're going to use. So we have some cities, which as you can see are the ones here. We have some countries. We have them here. We transform them into a list, as you can see here. And then we have some cost, right? So we have a cost from each city. How much does it cost to deliver from Panama to Panama? It costs $10. And from Panama to Colombia, and so on. So these are the costs. But you can look at here that we are doing some transformation. So we have like a dictionary of a key value thing, where the key is a tuple between the city and country. So here we will have for example, from Lima to Brazil, it will cost 30. This doesn't match this, sorry. But okay, let's continue. And finally, we have a limit of warehouses that we can build only 2 warehouses. So that was what we were told. We can only build 2 warehouses. So we'll see which ones are we going to build. Okay, so let's begin with Pyomo. So here is how we define a Pyomo concrete model. It's pretty simple. We just use the concrete model from Pyomo. And now we have to define our variables. So we have two decision variables, which are x and y. We will look now what is each of them. So first we can see that x is going to be the fraction of the demand for each country that we're going to serve from each warehouse. So for example, the same as before, Bogota is going to attend 20% of the demand of Peru, and that thing. So that is going to be our x. That 20% will be the value of it. So when we define that variable in Pyomo, we need to define the combination of the two possible lists or sets that we're using. And so we have kind of like, this is going to be the key, and then Pyomo needs to find the value of it, right? And we have another constraint of it. As we know that it is a percentage, so we have to bound it. So it's bound between 0 and 1, so it can be a percentage, right? Okay, so let's continue. We go to what is y. So y, if we pick a city or a warehouse, that would be a 1. It means that we are going to build that warehouse. So that's going to be the other decision variable. And as I told you before, this is going to be a binary variable, and it will be the binary variable will be for each city. So if we build Ciudad de Panama or not, Bogota or not, and so on. Okay, I hope everything is clear up to it, and let's continue. Okay, so now let's define our objective and our constraints. So here we have kind of like the mathematical definition. I'm not going to dive into it. Here we have what each of them means. So first we need to minimize the cost. So this is going to be 1 and our objective function. So let's see how we build our objective function. So we use the objective method from Pyomo, and let's see how we do to minimize that cost. So we have an expression here, and we see that we are summing over all the multiplication between cost and the fraction that we're using. So that is the proportional cost I have told you about. So look that this is only a function that returns a single scalar value. Sorry. So we can return a mean, the sum of it, and many other things that end up into a scalar, right? And we have to give it a sense. So we do not know if we want to maximize or minimize. So here we want to minimize. So here we have defined our objective variable. Okay, so let's continue. So the first constraint that we have here is that we need to satisfy all the demand. So this is kind of like the definition. So let's look at it. So when we look at this, we can see that on the model for each country, we must satisfy that it will be the 100% of the demand. So this is kind of like the sum of all the fractions of this country must sum up to 1. So I have to obtain the 100% of the demand of each country. So here we have defined the function, and we will look at this, and this is kind of like a condition. This will end up into a true or false thing. So that is how we define constraints, as we are comparing things, right? So we plug it into an attribute inside the model. We call it customer's complete fraction, or fulfill the demand. And we just put that the constraint, as we use here for each country, we must to pass all the countries here. So we will be a list, so we can kind of like do a broadcast on it. And next, we will define the rule. And the rule is going to be the function that we have defined previously. And it has to be like a conditional, so we need to end up with a true or false. So that's our second constraint. And let's look at the other constraint. So our other constraint is that we can only use build warehouses. So if we have not built it, we cannot fulfill demand from that warehouse. So let's look at it. So when we're looking at it, we can see that the demand fraction should be less to the y. And if we remember what was the y, it was 1 or 0. So if y is 1, is that we have been using it. If it's 0, we're not using it. So x should be used if y is up to 1. And we can see that it goes for each city and for each country. So let's define the constraint similar to before. We just declare the constraint thing, and we just put two lists or two sets here that we're going kind of like to iterate over it. And next define the constraint. We can also see that the constraint is a comparison. So we have here a true or false, and that's it. So we have defined our third constraint. Now let's look at our warehouse limit constraint. So we can only build up to two warehouses. So let's dive into it. So here we have it. So when we look at it, the constraint is just the sum, that when we go up to the sum, we need to ensure that it's less or equal to that limit warehouses that we have defined previously. So that is our fourth constraint, right? And now let's solve it. And I am doing anything with the 5 and the 6 because they have been previously defined here with the bounding and the type of variable. And okay, so let's use a solver. So this is an open source solver. It's called GLPK solver, which means GNU Linear Programming Kit. This is a linear programming, this is a mixed integer programming problem. So we're using this GLPK solver works pretty well for solving large scale linear programming and mixed integer programming problems. So let's look at how it solved it. So let's look at it. So we have here our two decision variables, our x and our y. We have here that it told us that we should use Ciudad de Panama and we should use Rio de Janeiro, right? And when we look at the x, how much demand fraction is going to attend each of them? So Ciudad de Panama is going to attend the 100% of Colombia, Guatemala, Panama, and Peru. Oh, that's cool. And let's look at Rio de Janeiro. Rio de Janeiro is going to attend Brazil, right? And when we look at the objective function, we know that it was $420. So let's look, that's the value that Piomo said. So let's look at the data if it matches. When we sum up to it, if we have 100, 200, 300, 380, and 40, 420. So that matches. So that is the optimal warehouse usage that we can use to attend all the demand, minimizing our cost, right? So that was the solution using a concrete model, right? So let's solve the same problem but using an abstract model. So what would it change? So this is the same as before. So we have our cities, a list, and so on. And here we're defining our abstract model. So as I told you before, here in the abstract model, we have not defined any values or dimensions. We just define it in an abstract way. We do not know the shape. So when we go up to it, we see that the model, we just change concrete for abstract, pretty simple. And when we just define the cities inside the model as an attribute. And we put it as a set. This would be kind of like a list. It can be, you can pass a parameter if you want it to be order for time series, for example. But we will use a set because we don't care about the order. We just need to know which cities are. The same for our countries. This is a set. And here we look another thing. We have here a parameter. So what is a parameter? The parameter method in Pyomo. So when we pass the parameter, we're going to have kind of like a key value pair. So what Pyomo is going to find are the values, but first we need to define how many keys we're going to have. So here our keys will vary with the cities and their countries, similar to the cost that we have here, that it's kind of like a tuple, and then we have the cost, which is the value. So that is our cost definition. Then we go up to our limit warehouses. So that's the param, but we have no keys there. We just have a single value. So we just define a single param, right? And when we define the model, we do the same as before. But now we're not using the cities, which were actually a list. We're using the attribute inside of it. So we just define the x and y with the attributes and with the same constraints. Oh, that's pretty cool. So, and that's the only thing that we need to change from concrete to an abstract model. Then, okay, so how do we pass the data now to an abstract model? So this is like the Python approach of passing the data. There are some other approaches, but I'm not going to talk about it. So let's look at this. So here we have the same data as before, the cities, the countries, and the cost. And it's pretty much the same thing, list, and a dictionary. And we have here defined data. So why this is, we can look that this is a dictionary. It has a dictionary with other dictionary, but what are they? Okay, so here we have a namespace 1 and namespace 2. So here we have defined kind of like two scenarios. So we can have this scenario. When we look at it, here we have 2 limit warehouses, and here we have 3 limit warehouses. So that's 2 scenarios. So we can kind of change between a scenario pretty easily. So let's see. And finally, here we define our variables. So you must see here a none, which is kind of pretty weird, right? But why is that none there? Because that variable does not need a key. So this is not a key pair thing. We just need, this is not a value thing. This is not going to be a value. This is just going to be the cities have, like the values are those cities. It's not going to be a numerical value, right? The same for the countries. And the cost, we have a key pair thing, because the cost, we have the key, which is the tuple that we saw earlier, and we have the cost, right? Okay, so that's cool. And our limit warehouses, we have the same, but we have no key, but we have a single value. we just put a single value because it doesn't have many keys to it. So it's just the default key for it. Okay, so now we have the data. So how do we solve it? Okay, so here we're going to solve how we create the instance, as I told you before. So we just plug the model and the data, and we here pick which scenario we want to run. We just create the instance. So that instance has now built in all the data and all the relationship between all the variables. So now we can solve it. So now we pass it to a solver. So we create a solver. We use the CBC solver, which is also an open source solver. This is kind of like bigger, but I'm not pretty sure about it. And then we just pass to that solver that instance, and we solve it. It will just raise the same result as before, but I'm not going to show you. Okay, so that's the warehouse problem. So now let's go into another example. So let's look at a Sudoku. So here we're going to do a Sudoku solver using Pyomo. Okay, so let's do the same approach. First, we're going to define the problem, then formulate it, then look at the mathematical modeling, but not too much into it, and finally, just solve it with Pyomo. Okay, let's go with it. So I hope everybody knows what a Sudoku is. So here we have like a Sudoku, which is the same arrangement, and here it is solved. So what we want to do is just to get whether a Sudoku we can solve it or not, and how many feasible solutions we can find, right? So that's the thing we're going to do. Okay, so let's go into it. So we need to find our three main components. So we'll go to objective later. First, we need to go to the constraints. So the constraints are pretty standard on Sudoku, that all values should be unique within a single row, all values should be unique within a column, and on each subsquare, all values should be also unique. And finally, a cell can only contain a single value. You can contain on a single cell 2, 3, and much more values. Okay, and what is our decision variable? Our decision variable is what value should we put in each set. So that is what we want to know. Okay, and what is our objective? Okay, this is a feasibility problem. So anything will work. We just need to fulfill the constraint. We don't care about the objective. We don't need to minimize anything. We just need to know if this is feasible or not. Okay, so let's see and do kind of like the formulation and the modeling. So here is how we're going to model it in Pyomo. So we're going to model it kind of like a cube. So we have kind of like some columns and some rows. And this is kind of like, if you look at the grid, this is kind of like the grid of Sudoku. And on the depth, we're going to have the values. So the values are going from 1 to 9. And that is going to be a binary indicator whether I use that value in that particular column or row. So that is the thing we're going to do. So this is kind of like a cube of binary indicators or variables on each cell. Okay, so that is what we're going to be y. So y is going to be whether 1 or 0. Okay, so now let's look at our constraints. So the constraint I have told you before, like for each row, we must ensure that every value is unique. This is this one. So for each column, we must ensure that every value is unique. This is this second one. And the third one is that for each square, we must ensure that all the values are unique. And finally, we must ensure that the values are unique per cell. Like whenever we have a cell, we can only have a single value. So these are our 4 constraints. Okay, so now let's plug it into Pyomo. Okay, so here we have a Pyomo. So we're going to do this in an abstract model. So let's look at it. So we define our abstract model, then we define a board. I will go up to it later. And then we define our rows, columns, squares, and values. Every each of them is going to be arranged between 1 and 9, because those are the possible values it can take, right? And that's it. So we have now our 4 of parameters. Okay, and now define our decision variable. So our decision variable is going to be y, and it's going to be a binary variable. So we have here, and that binary variable, we want to know that it's whether 1 or 0 for each row, column, and value. If I have to pick that value for each particular cell. Okay, so let's look on how to define our objective. So our objective and our model. So as I told you before, we don't care about the objective. We just put a 1 in there. We just need to know to fulfill all the constraints. So let's look at the constraints. So here we have pretty much the same constraints. So we define the row constraint, like for each row, each value should be unique. We just plug it into this constraint. So for each row and each value, we fulfill that it will be unique, right? So this is the first constraint that I told you before. Then we have the column constraint, which is pretty similar, but just changing for the column, the same here. And finally, we have the subsquare constraint. Here we defined previously what a subsquare is, kind of like the ranges. I'm not going on it. And just is the same. For each subsquare, I must ensure that each value is unique, right? And we define here the constraint. And for the value constraint, we have almost the same, which is for each cell, for each pair of row and column, we must ensure that each value is unique. Okay, so now we have completely defined our problem, so now we just need to solve it, right? Okay, so let's look at the board, as I told you before, that we just defined here a set, but why a set? It actually is a matrix or something like that. So let's look at it. So how are we going to define a board? So here is the definition of a board. So I have here an example. So it's going to be a list of tuples. And each tuple is going to be the row, the column, and its value. So when we look at this 5, 1, 5, we look at the row 5 and the first column, we need to have the value number 5. So here we have it. And as we can see, we didn't define all these zeros here. So this is kind of like the definition of an sparse matrix or the board as a sparse definition. So that's how we're going to define the board. Okay, so let's solve it. So now, as we know, we use an abstract model, so we need to instantiate it. So we pick a data, similar to before, I just pick a Sudoku, and we just create an instance of it. So when we have an instance, we have defined it. Okay, and we have defined all the relationship and some variables inside it. Okay, but as I told you before, I just defined here the board with row column value, but we need to change it into a binary definition. So that is what we do here. We build that model. So when we do that building, we just change the sparse definition into kind of like a binary cube definition. Okay, and then we move on. So we need to find multiple solutions because a Sudoku can have multiple solutions. So we need to store all of them. Okay, so we have a while true because we don't know when we're going to end if we find infinite solutions. So let's keep going. So we're using the GLPK solver, and here we do the solving thing within this context. So we solve that model with that instance of Sudoku, and we got a result. So when we got a result in Pyomo, we can have many termination conditions. So here we stop if the condition is not optimal, or if I couldn't find a solution, or if I just find all of them. Right? So we keep moving, and here we have something pretty weird. What is this at integer code? What are we doing here? So let's suppose that we have find a solution. So we need to find the next one, but I already have a solution. So if I just plug in that model with that solution into the solver, it will tell that I am the same point. I have a solution. So I need to add a constraint that, hey, this solution, you cannot give me the same. You need to give me another one. Or if you don't find another one, just end. And I don't find any other. Now here we append the solutions, the instances with each solution, and let's look at it. So here when we execute it with that Sudoku that I told you before, so we found two solutions. So now let's look at it. Okay, so here are the two solutions. So here was the initial Sudoku, and here we have the two solutions, the two possible solutions that Pyomo has found. So we can see that these 3 changes and these 7 changes, and there were many changes at the bottom. So for example, this 4 and this 7 and so on. And it fulfilled all the constraints according to Pyomo. So that's how we solve a Sudoku using Pyomo, which is a constraint optimization problem. A constraint problem, sorry. Okay, so let's do a recap and a summary of Pyomo and the presentation. So first, we just do the definition of an optimization problem. We have 3 main components: objectives, constraints, and variables. That's perfect. Then we do a Pyomo overview. That is open source, it is solver agnostic. We have used 2 solvers here. We didn't even care which solver and how it may work, but we need to read about it because you cannot use a solver for nonlinear programming to a linear programming, or a linear programming to a nonlinear programming is not going to give you a really good result. It has pretty nice documentation, and you can tackle multiple optimization problems, and it has many capabilities for doing different things. Okay, and what we have done, we have go to 2 examples. So we define 2 optimization problems, we use different solvers, and we display the solutions, and we can show our decision variables and how they behave. Nice. But that's not all. Pyomo has many other things. So it has really a really broad environment and with multiple solvers that you can do and multiple problems that you can solve with Pyomo. You can solve nonlinear optimization problems, general disjunctive programming, mixed integer nonlinear programming, quadratic programming, bilevel programming, algebraic equations, and so on. And also, Pyomo has many capabilities to help you with some cool things, which are sensitivity analysis. You can do block modeling, like plugging different things or different kind of model when you do kind of like a big model with different kind of like parts, and you can pick which of them you can choose, right? And that is much of Pyomo. So just what I wanted to show you is how pretty good it is on Pyomo, and that we can use it for solve many things. Commonly, we use a lot Excel, but this is much more kind of like, I don't know how to say that. It's really powerful. So we can use it for different multiple problems, and I hope this tool can help you a lot. And also to thank the Pyomo community and the Pyomo maintainers and contributors, because this is an amazing tool. And that's all. Thank you very much. So here is the repo. If you want to look at the examples on a notebook, I have some couple of examples that are a nonlinear programming example, and I forgot the other one. Okay, but it's an extension of the warehouse problem and so on. You can go at it, contribute, maybe put more examples on it. Here is my contact in LinkedIn, and so Factor is hiring. So I hope everyone finds really cool to join Factor. We're hiring a lot of people. We're mainly focused on data science things, data engineers, data scientists, machine learning engineers, DevOps, backend developers, and so on. So just to, if you like to join us, you're pretty welcome, or contact me or contact Factor if you want to know more about it. And that's it. Thank you very much. Here are kind of like some references of Pyomo where you can learn about it and look deeper on it, because it has really a big thing where what you can do with it, and it's pretty robust. Thanks.